my...
Yes, we
Okay.
can see your slides.
Okay, so firstly, thank you for inviting me in Crypto Cafe. And I'm Sohyun Jeon. And today I will talk about our lattice-based scalable threshold link signature, LastRing, which is the result of my internship program in entity. So link signature is a scheme that allows the signer to remain anonymous inside the group of users. And this group of users is called link and noted as R. So the verifier outside the link cannot know who is exactly the signer. And threshold link signature is an extended notion of link signature. So it allows the T signer to sign the message, and still the verifier cannot know who is the signer. And threshold link signature is useful in privacy-preserving systems such as electronic voting, whistleblowing, and cryptocurrency. For example, cryptocurrency use blockchain these days, and blockchain for the decentralization, because before blockchain we should give our information to bank or government for transaction. But using blockchain, we can transact anonymously. So in cryptocurrency, for anonymous, TRS can be used. And in TRS, the signer needs a sufficiently large link to hide their identity. So if the link is larger, then it is hard to find the real signer. And most TRS schemes have link-dependent signature size, because in this scheme, the signer firstly generates its signature. And to hide their identity, they also generate the fake signature for the link member who is not signer. Then the signature is the collection of them. So its size is linear to the link member. And there are improved results with whose signature size is linear to the threshold, and threshold is less than the link size n. So in this scheme, the signer generate the zero knowledge proof. So the proof doesn't contain any information about the signer, so they don't need to generate a fake signature. So the signature is just the concatenation of T proof, so it's only linear to the threshold T. But this scheme needs extra property to prove the distinctness of signer. For example, linkability, which tell if there are two signatures, then whether the two signature is generated by the same signer or not. And the signer's identity is still keeping anonymously. So our goal is constructing a more compact lattice-based TRS scheme without extra property. So we are inspired by aggregate signature using Falcon and LaBRADOR. Falcon is lattice-based signature scheme selected by NIST, and recently it changed its name, but today I will just call it Falcon. And it has small signature and small public key. Also, its signature generation and verification algorithm are efficient. So in the table, there are least candidate signature scheme, and Rainbow has really small signature size, but its public key is extremely large. And in contrast, the Picnic and Sphinx had small public key, but large signature. And Delicium has smaller than Rainbow, Picnic, and Sphinx, but it's still larger than Falcon. So Falcon has advantage in the multi-user setting, because in multi-user setting we should collect multi signature and also public key of user. So in aggregate signature, after signing a message, they generate a proof for the aggregated signature. And for small proof size, they use the lattice-based succinct argument LaBRADOR. So we also use Falcon and LaBRADOR, but aggregate signature actually don't need to hide the signer's identity. But in TRS, we should hide the signer's identity. So we need a zero knowledge property, but actually LaBRADOR is not zero knowledge property. So we also use LMP, which is the lattice-based zero knowledge argument. So now I will explain how our scheme works. So before our scheme, I will briefly explain about the Falcon signature scheme. Falcon's public key is sampled from NTRU distribution, and secret key is the trapdoor to generate a signature. So using secret key, the signer generates a small ring element S1 and S2, satisfying this red equation. And then verifier check the signature satisfying that equation. So in our TRS scheme, user's public key and signature is the same with the Falcon's key. So using Falcon scheme, each signer I generate sign the message. So it means they generate SI1 and SI2, satisfying the Falcon's verification equation. But the Falcon modulus QF is too small to use proof system. So each signer compute the ring element Vi, satisfying this equation to convert the equation over the ring of proof system. So for modulus QF, it SI1 and SI2 still satisfying the Falcon's verification equation. But here HI is the signer's public key. And for anonymity, we should hide the HI. So we set HI as a secret information WI. Then the Falcon's verification equation is changed to the equation 1. And WI is actually one of the public key. So we can express it as a inner product value between a public key vector H and a binary unit vector delta I. And delta I indicate the user I's public key HI. So I's component is 1 and the others are 0. So when we computing the multiplication of H and delta I, we can get the HI. But delta I also indicate the signer I, so we also set it as a secret information. And then we prove that delta I is a binary unit vector. The first equation tell the delta component of delta I is 0 or 1. And then second equation tell the only one component of delta I is 1. Yes, so, and then delta I should indicate the different signer for distinctness. If delta I indicate the same, if we cannot prove the distinctness of signer, the one signer can generate the whole signature of other member. So it is the important part of TRS scheme. And the third equation tell the delta I and delta J has a component 1 in the different place. If they have the 1 in the same place, their inner product value will be 1, and then the summation would be larger than threshold T. So this equation tell the delta I and delta J indicate the different signer. And so now the signer should prove that they have secret information WI bar, which consists of SI1, SI2, VI, WI, and delta I. And it is secret information to anyone outside the signer set S, but it doesn't contain any secret key of the signer because SI1 and SI2 is just Falcon signature, and WI is ring element to convert the ring, and WI is actually HI, which is the public key of signer, and delta I is just indicator vector. So the signer can send it to each other. So the signer firstly pick the leader, who is the one of the signer, and then send WI bar to the leader. Then the leader will generate a proof for the secret information WI bar. So collecting all secret information WI bar, the leader should prove that the WI bar satisfying this or equation. And these equations are quadratic. For example, first equation contains the multiplication of WI and the SI2, and both of them are secret information. So this equation is quadratic for the secret information. So we need a proof system for quadratic relation. So that's why we use the LaBRADOR and LMP, because both of our argument for quadratic relation. So now I will explain two proof system and how the reader use them. The LMP can prove that the witness S1 satisfying the quadratic equation FS1 equal to 0. And then the proof contain the opening ZI, and ZI also satisfying this equation for verification. I just skip the detail, but what we only need to know is the ZI also satisfying the quadratic equation. And then LMP use rejection sampling to hide the information about the SI. They add the random vector YI to hide the distribution of SI. So it has the zero knowledge property. But ZI has the same dimension with the witness SI, so its proof size is linear to the witness. And LaBRADOR also can prove that witness satisfying the quadratic equation, but its witness is the same dimensional vector, and the opening Z is linear combination of them. So, and Z in LaBRADOR, Z also satisfying the quadratic equation. And Z they don't use the rejection sampling, so Z doesn't hide the information about the WI, so it doesn't have zero knowledge property. But its purpose, but its purpose size is smaller than the witness because uh, the dimension of Z is smaller than the witness W prime. And moreover, the prover can reduce the proof size by recursion. Since the Z satisfying the quadratic equation, the prover can set Z as a new witness for LaBRADOR. And then the prover recurs the proving process. Then by repeating the recursion, they can get the logarithmic proof side. So LaBRADOR is a succinct proof system. So in TRS, to hide the signer's identity, we need a zero knowledge property. So we use the LMP. But as mentioned before, the proof size of LMP is linear to the witness. And in our scheme, the dimension depends on the number of ring member n because of delta I, which is the n-dimensional binary unit vector to indicate the signer I. So we need some modification. And then we know that the verification equation of LMP are also quadratic. So we combine LMP with LaBRADOR by setting output of LMP as a new witness for LaBRADOR. And then LaBRADOR has the logarithmic proof size. We can reduce the proof size. But we should check that it still have zero knowledge property. And for zero knowledge, we should construct a simulator and then check the adversary can distinguish the valid proof and simulated proof. And constructing simulator is easy in our case. Firstly, simulator run the LMP simulator. Then it can get the LMP proof without the witness. And we set Z1 and Z2 as a new witness for LaBRADOR. So simulator can learn the LaBRADOR proving process. And then it can get the LaBRADOR proof. So through this way, simulator can generate a proof without witness. And now if the adversary can distinguish the simulated proof pi from valid proof, it means the adversary also can distinguish the simulated proof of LMP. So by the zero knowledge property of LMP, the combination proof system also have zero knowledge property. So now using these two proof system, the reader generate a signal, the threshold signal, ring signature. Firstly, it generates a LMP proof and then set Z1 and Z2 as a new witness for LaBRADOR, but Z1 and Z2 has different dimension. And we should set it as a same dimensional vector. So the reader split Z1. And we know that the Z1 is the opening of concatenation of all secret information. And then for convenience, we will split it into the part of opening for each secret information. But they still have different dimensions. So the reader padd 0 to them and then set padded vector as a new witness vector Wi prime. And with Wi prime, the reader generates the LaBRADOR proof. So finally, the signature consists of the pi bar, which is the constant part of LMP. Its size is constant, so we don't need to reduce the size of it. So we only set the Z1 and Z2 as a new witness for LaBRADOR. So the final signature contains the constant part, and then pi prime is the LaBRADOR proof. And since LaBRADOR has logarithmic proof size, our signature size is also logarithmic to the threshold t. So now I will show you our signature size. So we compute our signature size for different parameter, the number of ring member n and threshold t. And pi bar is constant part of LMP, so it has the same size even for the different n and different t. And pi prime is LaBRADOR proof, and it only depends on the threshold t, so it has the same size for the same threshold t. And since LaBRADOR has logarithmic proof size, our signature size is less than 150 kilobyte, even for the large ring and large threshold t. And we also compare our result with the previous TRS scheme. And they reported their proof size for different parameter. So we also provide the two results for n equal to 100 and 2 to the 10. And here is the T is half of ring member N. And above four scheme have megabyte signature size because it's the first, in the beginning I mentioned two types of TRS scheme. First one is the generate a fake signature for all ring member. So it's linear to the ring member number n. So its size is it has megabyte size. But even for the same ring size n, our signature size is 122 kilobyte, which is much smaller. And the signature of fifth scheme is actually the concatenation of T proof. So it is the second type of TRS scheme. And they only reported their proof size, which is the 1.2 kilobyte. So we compute their signature size by multiplying threshold T. And since its proof size is small, its signature size will be smaller than ours for threshold T less than 100. But its signature size is linear to the T. So if T is over 200, which is not extremely large in TRS scheme, its proof size, its signature size also over 200 kilobyte, which is larger than ours. But our scheme still have less than 150 kilobyte even for the large ring size N and also large threshold T, which is over 500. So our scheme is more compact than previous scheme, and also our scheme is suitable for scenario requiring large ring size and also flexible threshold T. So yeah, thank you for listening.
So I have one question as of now. So
Okay.
you need to do some form of rejection sampling in the construction, if I understand correctly, right?
Yeah, yes.
So I'm just curious, how do you do like how do you simulate signatures when something is queried by some challenger? Because you're already committing to like you are already committed to something. Then if you have to do the rejection sampling, you might not end up doing the simulations where the signature is queried for. So this is kind of a tricky thing I felt. So do you have any intuition?
Yeah, actually, the rejection sampling is the challenge for computation, but
Mm-hmm.
actually, our work is focused on the proof signature side, not the efficiency of algorithm.
No, not efficiency. I'm saying in the proof, in security reductions. When you do the security reductions, like the unforgeability reductions, for example, okay?
Uh, yes.
So in the unforgeability reductions, like a challenger can query signature for any message, right?
Mm,
Now, because of the rejection sampling, you might not generate a signature where the query was being asked. And then you have to somehow send something like null or something. And then it's like, I not want to give you signature for a very specific message. No?
You mean the rejection
Because
sampling
of the rejection
can
sampling, like you have to drop some instances of the query.
of the query?
Yeah, yeah.
But rejection sampling is uh, uh, executed after the prober get the challenger C, because the proof actually the LMP is the interactive protocol, and then we use the Piaget technique transformation to change
Into the
the
signature.
non-interactive proof.
No, like in normal Fiat-Chami signature, I understand. Like you get the challenge and then you just do the simulation. That's very simple. That's a zero knowledge property of the signature. But now in the ring signature, because there are other members, right? So I'm a bit confused. How do you do the simulation? Maybe I have to think a bit. But okay, like this is I mean maybe it's a bit complex thing at the point.
Yeah, so that's why we set the leader. Actually, the threshold link signature has the multiple use signer,
Yes,
but in our scheme, they only the generators Falcon signature independently and
I
then
see.
collect all of them, and then the proof actually generate of proof is work of leader. So only
Okay,
one person. So yeah.
I see. I see. Any other question?
Just on your last table, I was wondering if there was a typo when you say for the threshold n/2, the proof size of CDD is 1.2. Is it megabyte or kilobyte?
The size of CDD?
Yes, when you say that when t is n/2, because it's 1.2, because 1.2 kilobyte mean is very small.
1 to 2. You mean our signature size?
No, the one below the caption below
Caption.
table.
Sorry, which one?
In the caption, you have t is equals to n/2, the proof size of CDD plus 20.
Yes, it's 1.2 kilobyte. So if the threshold t is less than 100 or 100, its signature size will be 120 kilobyte, and it is similar with our signature size.
Okay,
But
120 kilobyte. Okay.
yeah. But if t is over to 150 or 200, then its signature size is linear to the t, so their signature size also over 150 kilobytes, but our signature size is still less than 150 kilobyte. And here's the threshold t is over 500 because t is the half of the n.
Any other question? Okay, so there is no other question. So let's thank Sohyun for her beautiful talk at Crypto Cafe.
Thank you.
Thank you.
So that's it for today. So hope to see you sometime soon, Sohyun. Thank you so
Okay.
much.
Thank
Bye.
you.
Have a good day. Good night. Bye.
Bye bye.